Very formal announcement.
Yes.
Nope. Hey, Jim.
Guys,
Lawrence.
okay.
So this is, I guess, drinks and gears.
Drinks and gears, yeah. Well, I'm not sure that's a safe thing to mix together, but we'll see.
Definitely.
Well, Jim seems to think it's okay.
Yeah.
Yeah, it's fine. Belgium Leffe.
Belgium.
I think it's Belgium, isn't it?
I think so. Yeah, it's a wheat beer, isn't it?
I think it is. Yeah. It's something different for Saturday, you know?
Yeah, definitely. Cool. Right, we've got recording going, which is good because that's a bit I normally forget. This is actually session 4, which we did 3 of these sessions previously, which were on YouTube. So I'll post some links on that. So if you're joining for the first time, we are going to jump straight in the middle of it, but you'll still pick up bits and bats. And if you've got any questions, I want to stop anything or ask anything, then just fire away. What we're doing, I think we are building a tool, and is it Chopper we're building it for, Tim?
Well, it's actually the base design was taken from the Mark III full-size astromech, and that's kind of the infrastructure that I'm building to, with the hopes that this tool base can be used for someone to design a tool that's different from the interface and the gripper that's available widely, just to allow them to mix it up a little bit. So, but I stole the lifter and mech from Chopper. So it's the exact same lifter mech as Chopper, but it'll fit in a full-size astromech, but I'm also being selfish. It's also going to go into our Duo. So this tool is going to end up in him. So it's going to be Chopper sized, but you can easily extend this tool to the full Mark III sized astromech.
Cool. Okay, do you want to? Well, we can get started now, Tim. If you want to share your screen.
All right, share screen. Looking for Fusion 360. Here we go. So is that sharing to everybody? Oh, I guess I have to click share. There we go.
It works after you click share.
Yeah, weird. All right, so I'm wondering why I don't see my browser.
Are you sharing Fusion 360 rather than your desktop?
I'm sharing, but I thought it was Fusion 360. Let me try this.
Yeah, if you share the Fusion 360 app, you don't see the browser. Whereas if you share the desktop, so the whole PC, you'll see the browser. It's a bit of a Fusion 360-ism.
Share screen and desktop 1, I guess.
There we go.
That looks. Oh, here we go. Okay.
There you go.
So we'll just go full screen, I guess, on that. Everybody still see it?
Yeah, it's working.
All right. So just a little quick overview of where we are. What we're trying to do is build a tool for a generic Mark III astromech. So with that in mind, I started with the base interface arm servo base, or just a basic piece that fits into the astromech as currently built. And then I decided what I'd do is I'd jazz it up a bit, and I took this bearing that I made for Chopper's arms, his head arms, and use that as the basis of the rotation mechanism to make it nice and tight and smooth. And although I don't use this in Chopper's tools, this gear ratio is the same as Chopper's. In fact, I stole all that right out of Chopper. And up until this point, what we've been doing is just modifying the pieces to fit in the astromech version Mark III. So last time we left off where we had built the interface, so to speak, of the, let me just hide a few things here. Chopper arm bearing. So the concept was we were going to use a magnet to mount this piece onto, or mount the arm onto the astromech. That way it would be able to be easily moved on and off the droid and not very fiddly to assemble and try to screw in. And so this little cavity here and interface will fit the magnets, which you can buy off of any magnet place that sells magnets with holes in them. And I've got these particular ones picked out. That's what these are here. Those are actual 3D models of the magnets. So here's where we kind of left off. It was in this state, and we were trying to build the top of these this arm in a nice fashion. So what we'd done is we projected a few arcs and sketches, and we were going to do a loft. So to do that, before I go into new content, does anybody have any questions of how we are, or before I launch in? Is everybody sort of caught up? Any questions as I go too fast?
Nope.
All right. So here we go. We're going to create a loft, and lofts can be tricky. So I want to go from here to here to here, and you can see as it draws that it doesn't get the right shape because it's just swinging it around. And what I really want to do is follow that shape. So I need to add a rail. So I'm going to click on the rails button and then choose this as my rail. And it works perfectly. If you get an error, let me show you what error you're likely to get with this particular sketch, because I got it a few times and was causing me grief. So I do this to do my sketch. If you have chain selection, which is kind of the default, this, and then I pick my rail, it's going to give me an error. The rail is not smooth. And the reason is, if we kind of zoom in here and figure out what rail, it's actually choosing a rail. That's the whole shape. If I do that, and let me start again here. If I create loft, if I do this with my rail without chain selection, it just picks the actual shape of the outer edge of the piece I'm trying to make. And that error is very frustrating. And if you're not aware of that, it'll cause you lots of grief. So with that in mind, you can see it gives me a perfectly aligned, perfectly shaped thing. Last time we kind of cheated. You could do this body with a rotation also, but if your shape was not perfectly round and not perfectly rotatable, this loft command is going to be your friend. So operation is join, and boom, now I have the top of my arm built. So the next part is to join this part with this part. There's a couple of ways of doing this. Here, I've just, in this body, we created this before. Let me turn magnet spot off. Let's turn this gear off so we can look at what we got here. So that's just an extrude. Like that's too far in advance. So let's go back to magnet spot. So here's where we want the arm to terminate. You can see we got a little problem here where this is going to be creating some weird geometry. So what I'm going to do is just take this part here. I'm going to hit the Q key, which is offset face. I'm going to drag a little bit and then click on where I want it to go. And actually, let me do it a different way. I'm going to do the extrude command. Extrude. It's going to actually do the same thing, but it's going to offer me a chance to make a new body. So I don't want to join that. I want a new body. And then we can take our magnet spot. Let's hide that for a second. And then I have this piece here, but I don't really want that. I want to have a solid. So I just hit the center area there, hit the delete key, and that deletes that. And I'm just going to drag this out as such. And now I can join those two together. And now I have a nice, nicely formed 90-degree angle that matches up perfectly to where I want this magnet to go. So for that, I'm going to use the Q key again on that face, drag it back. Oops, I don't know which I've got the right spot here. Q. You know what I did when I joined? I kept tools. So instead of having, so this is a not a common mistake, but an easy enough one to make. So if you remember back when I hit the combine command, keep tools, this little checkbox. So it created a copy of my original arm, and that can be confusing. So let's just delete that, and you can see we've got that part. So that's why it was acting weird. So again, back to the magnet spot, select this, hit Q, and just drag it back here, and then snap it to that face. And now we have a spot for our magnet to live, and we can combine these. Keep tools, I'll uncheck that. All right, so that is ostensibly the tool arm lined up with the magnet spot. Eventually, I'll have to go in and, although the magnet provides enough force to rotate with just the sheer force of the magnet, I might want to increase this a little bit to put some kind of a torque carrying mechanism, just a little spline or a couple of splines between these two so that the magnet doesn't have to do all the work. But we'll leave that for a little bit later. So that's kind of lofting. So the next thing we wanted to do is create a motion link and create some components. So you can think of a component as an entire Fusion 360 project all inside a single line on your browser here. So this MS Lifter Servo R is a component. You can tell it's a component because it's got this little box that shows up, and you can activate it. When you do, that becomes the active component, and every cut, copy, paste, every sketch, every new object will show up inside this component. And you can also do motion joints and, like I said, a complete project inside a single element inside your browser. And they're very handy when you're working with complicated things. And if you want to do any motion and or movement studies or tests, you have to have components because they're the only ones that can work with joints. So right now I've activated this servo, and as you can see, my servo has the disk and the servo, and this is just for reference. So when I'm building models, I can target that geometry. So let's go back and activate the main component up here, and now everything else comes back in. And now anytime I do any work, it's going to show up in the main document, or the main, the main document. So right now, the 44 tooth gear is a component. We did that in a previous lesson, but this 72 tooth gear is not a component. So let's make it one, because we want these two to interact with each other. So it's simple to do. Just right click on it, create components from bodies. And this new component is going to go inside the current active component, which is the main project. So I'm going to just click on that and Shazam. There we go. Now it's a component. And as such, I can now work with, I'm just going to put these two next to each other just for ease of finding them. I'm going to put a joint on this component and put a joint on this component, and then we'll make them work together. So to put a joint, it's under the Assemble menu, and you just click on Joint. And now it's going to ask, where do you want this joint? And there's a couple of cool ways of doing it. You can see as I put my mouse here, it's going to float and try to snap to certain locations. Right now, it seems like it's on the outer edge of that gear, which I don't think I really want it on the outer edge because the gears are not lined up. Although in this case, it'll probably work. Yeah, we'll just do that. So assemble, joint, we'll put it right here. And then we're going to put, well, I've got, getting ahead of myself. This also needs to be a component. This interface arm servo base. So let's create a component of that. Create component. And again, we'll just move this up and so it's easy to find. So what we want to do is create a joint, rotational joint between these two pieces. So assemble, joint, and now I'm going to grab that as the joint location and the outer race as the other joint location. And now it's going to ask me what type of joint I want. Well, I want a revolute joint. And you can see that it's properly guessed what I meant. And you can see that the joint kind of doing its thing there, just spinning around in the Z axis. So that's all cool. Now I need to do the same thing with this other gear. So as recall, this is a component, and actually there's going to be an error, and we'll let you see the error as it comes up, or just not really an error, but a mistake. So the next joint we want to make is a rigid joint, and it's kind of a joint is built. I think that is even a joint is built rigid group. So we're going to make this. No. Well, let's see. So what I'm trying to do is make this and this live together. So to do that, let's drop down. I should have done this earlier, but my servo model doesn't have anything but bodies in it, so I can't connect to it as a component. But that's easy enough to fix. So let's go down to my servo, activate that. You notice how everything else kind of grays out. And then we'll look inside and we see I have two pieces, the servo body. Let's make that a component. And since the servo is the active component, the new component comes in inside. And the servo disc, what we're going to do is make that a component. Boom. So now this contains two components, the body and the disc. And what I could do while we're in here is make a relationship between the servo arm, which is this case a disc, and the servo, and we'll insert a joint there. 1 second, I need to ask my son to turn the TV down so it's not bleeding through in the background. Sorry about that. Can you still hear me? Hello?
Yep. Yeah.
Okay.
Yes.
So we're going to create a joint between this disk and the servo. So this right here and that right there, motion, rotate. And you really can't see it here, but you can see that that thing is spinning. So now that we've done that, we can go back to the main zapper assembly and continue with creating a rigid group between this and the servo arm. And that basically says anytime that servo arm moves, the gear is going to move. So let's not get too far ahead of ourselves. So what we've done here is we've got a joint, Rev1, and rigid group. And inside of our servo, that's the servo base. The servo, we've also got joints of Rev1. So you can kind of click on it. You can see how it highlights in blue there, dark blue. And then this Rev is the other one. So what I can do now is drive joints or just animate joint. And you can see that's animating the joint. But what I'm going to do is animate model. And you can see now my gear is spinning. Actually, the gear is spinning because the servo arm is spinning. So these joints, servos, and this is not a 360-degree rotation servo. It's probably a 180-degree rotation servo. So what we can do is put a joint limit on this. And so we'll go to edit joint limits. And we want a minimum, a maximum, and a resting spot. So for the maximum, make it 90 degrees. And so now this, when you animate this, it should go to 90 degrees and then back because you can only move 90 degrees. And just hit the escape key to get out of that. So these two gears are interacting with each other. You can see when I rotate, when I do any of this animation stuff, they're not reacting to each other. Well, because they don't know about each other yet. So let's first make it look pretty. So let's take this gear here. And I'm just going to move it. And there's maths to do this, but I'm going to go body and click on this body and just kind of rotate it so it looks right. And that doesn't need to happen, but it just makes me happy. All right, so now what we need to do is do something called a motion link. So we go up here and we go down to motion link. And we want to motion link this joint to this joint. Oh, look what happened. I knew this was going to happen. Yep, they're both linked together, but we have a problem. The problem is this servo is not mounted in software to that base plate. So we'll go back to assemble, rigid group, and we pick that component and that component. And now those are tied together. And now let's go back and try our motion link. This one to this one. And why is it not moving? Oh, it's only one selected. That's why. 1, 2. There we go.
Celsius at one point represented that they're expansion.
I couldn't hear you. Say again. I didn't hear the question.
So I wasn't sure it was a question or was it background noise?
Well, it doesn't seem to be so. It may be just the background noise. So at this point, if I go to animate joint, that doesn't work, animate model, you can see, well, we've got a problem. The gears are scrubbing each other. So let's go back up to our motion link and edit it. And let's click on reverse. I think that'll do it as far as, or basically for every 1 degree this moves, this is going to move 0.6 degrees. Oops. And let's see what that looks like. There we go. So this is a 0.6 to 1 ratio, just the number of teeth divided by that. It turns out to be 60%. So now I'm going to hit drive joints. And when I move, actually, that doesn't look quite right, does it? So let me, my math is probably off a little bit here. So we got 44 to 72. So 44 divided by 72, that's 0.6. 1.
Hey,
But for some
Tim,
reason, yes.
could it be that you need to put negative 0.6 degrees? Does the
Well,
sign matter?
it does. And I had the reverse, which should do that. See, the reverse puts the negative in there for you. But it should. Something funny is with that ratio. This works on my test case. I don't know why this is acting wonky here.
The ratios of the gears backwards.
Ah, thank you. So let's go to edit and make this 0.61 and this 1. And now, thank you for that. Drive joints. There. So we're almost done with, we've got our servo driving our lifter gear, but now we have to connect this to this, but this is a body and it has to be a component. So we'll go to lesson arm, create component, and that's it down here. And we just assemble rigid group this to this. And this little button, this little check mark here, can create problems because you may grab things that are supposed to move and now they're rigidly locked. So I generally don't have that connected unless I know for sure the sub components need to be rigid with that group as well. So drive joints. All right, so you can see it's working, but it's working backwards. So why is it working? And just to show what I mean, if we go back to our beginning part here, you can see it's when I rotate it, it's going backwards into the droid. And this is again just a joint limits problem. It looks really good. It's just my joint limits need to be reversed. So this one here, edit joint limits. So when I move it, it probably should go that way. And let's see what it looks like now. Voila. Now, you can see here, when I go 90 degrees, it runs out the top of the droid. That's fine. When I go the other 90 degrees, or the other limit, it stows nicely exactly where I want it to. So when I control this in software with Maestro or PCA 9685 or whatever, that's going to determine the limits of travel. But what I'm doing this whole exercise for is to make sure that my mechanism can travel well within the range of where I want to put it, within the constraints of a typical 90-degree rotation, which is like Mark Arduino uses 90 degrees for all of its servo movements. So if you have your droid tuned or your model tuned so that it moves 90 degrees and does a proper movement, then you're kind of ahead of the game. And if you have any other control system that allows you to change how far you're driving that servo, you know that tool is going to do what you want it to do. All right, so that's fast and furious. Let's open up for a few questions and see if we can catch anybody up if I've gone too far or too fast.
I noticed you were having to go back and forth when you're animating to look at the other side. Is there a way to animate the gear while still looking at the other side, like sort of the gear is out of view?
So you can animate model, and it's going to run through the joint limits. So now I can just pan and scroll. Is that what you're asking about? So right now that's, I'm not doing anything, I'm not touching anything on the keyboard. It's just running through the joint limit to joint limit.
Yeah, that's what I was thinking of. That's good.
And then to get out of that mode, you just hit escape and it goes back to, again, we'll look at the joint limits. The servo had one in it. If we go edit joint limits, you can see it's got a minimum, a maximum, and then a resting position. And the resting position is when you if you stop moving the servo, that's where it wants to go to rest, which is in the stowed position in our example. So that's kind of the basis of building the components and the joints and the motion link. And that was all done just so we can make sure that we're building a rational system, because if you can't test it, you'd have to print it out and find out, oh, the gear ratio's on, or it doesn't move far enough, or whatever, or you don't have enough throw on it. So once we've got that sorted out, we can kind of take a look at, well, what is this tool going to actually do? And with that, what I did is I brought in Chopper's interface arm and mirrored it. So you can see when I did that, what I did is I brought in an additional little servo that has this little disc on it that captures a filament piece or a guitar string. Use this set screw here to capture it, and then it allows you to swing that servo into this chamber and push it into the hole here, and that way, this was Chopper's interface tool. Just looks like that. Let me turn this find in browser. Turn that one off. So that was Chopper, or is Chopper's tool. And the reason I'm bringing this out is, oops, hit delete. I didn't mean to do that. I meant to hit V for visibility. And now my computer's thinking really hard, so give us a second. Fusion does this for some reason. Every now and then it just takes a little siesta. I think what it's doing is it's uploading to the cloud your undo file or your something.
Oh, yeah.
Oh, and after all that, it decided I couldn't do what I wanted to do. So what I meant to do is that V, visibility, and you can see how this has this internal chamber here for the filament to go and use this push rod. So the reason I'm bringing that out is, in my mind, we're going to create a similar tool, but we've already done the interface tool, so we don't need to do that. So let's turn all that off. Interface mirror. But we want to kind of build that. So how do we build that? So
Tim, a quick question, if you don't mind.
yes.
So the number of teeth, assuming that we're 3D printing, PETG or any other material, do we think that the granularity, and how fine those teeth are, is going to limit the longevity? Is it something where going with a slightly more coarse number of teeth would be of benefit, or no?
Yeah, that's always a consideration, is the durability of the plastic, the material that you're printing in. But I found that even like a PLA plus or a PETG are both plenty robust, because we're really, at the end of the day, we're not doing any real mechanical work. We're just lifting mere ounces or just a few grams on not a very, like, we're just not asking them to do much for us. The biggest strain is going to be would be on the old version, had just a bushing, basically, that there was no real bearing or anything in there. That's going to kind of wear out over time, whereas this design has an actual bearing using 6mm BBs, which will make this whole thing even less stress and less work required by the lifter. But the reason I chose the gears I did is to give enough granularity so that you could choose. I mean, because if you had just 2 teeth on it, it'd be up and down, and we want several locations in there. And you could probably get away with less teeth than I chose, but I wanted enough mechanical advantage and resolution on the movement of the servo that it would be smooth and natural in the movement. Did that answer your question?
It did. Thank you very much.
All right, back to, I tabbed back into, there we go. So here we have our model, and I want to show a couple of things that are required to build that path. So we want to create a path for a piece of filament that's going to go through this little hole here and end up here somewhere. So the first thing I did was I created, in fact, let me just find in browser. Here, this sketch here. I'll just delete that. I'll create a new one. So just for reference, we'll go back to interface on our mirror, and that's Chopper's limit of what will fit in a chopper, and also for our Duo. So I'm using that. If we wanted to use the Mark III, I've got that here as a reference as well. You can see the Mark III tools can be a few inches or centimeters longer. And that's just a matter of extending this tube and your tool at the bottom. But there's also some pretty big tools in R2's arsenal that maybe you want a slightly smaller arm. So let's turn that off, and let's turn that off. And interface arm. So now we're back to scratch. So let's go back to building our path. So the way I'm going to do this is I'm going to go create sketch. I'm going to put it on the bottom of my tube. And in the middle of that sketch, this center point is going to be preserved, but let's say we want a 2.2mm hole in there. And that's really just for reference at this point. It's not even going to be needed for what we're going to do with it. And if we wanted to split this in half so we could open it up and print it flat, let's create a splitting line, also for reference. And where do we want this to go? Well, we want it to go here. So we'll create a sketch here, and it's already got a nice hole built in for us. Okay. So now we need to draw a line from here to here, but we don't really have a convenient place to draw that line. So we can make one. The easiest way would be on the plane that's right here. So let's draw up a place to grab a plane on. So I'm going to go back and edit this sketch, and we want to put a plane here. So end sketch. How do I get a plane there? Well, construct plane at angle and choose that as my spot, and you can see conveniently it came in exactly what I wanted. If it didn't, usually it's 9 degrees, like sometimes it guesses wrong, but you can easily do plane at angle, pick the line that you want, and Shazam. Now I've got this plane can perfectly bisect this tube and line up right in here. So what we're going to do is create sketch on this plane here. And the problem is now we got all this junk in the way. Well, this is easily fixed. If I go to sketch, slice sketch, you can see it does an automatic cross section for me. And that makes my life a little easier. So I want to grab, you can see the spots kind of floating here. So I hit the project key and just, I'm going to rotate over here, make sure I'm getting what I think I'm getting. Yep, that's the spot I want. I want to project that, and I want to project either one of these. That is fine. And hit OK. So now I've got a ability to grab from here and go to here. So this bottom one, I'm just going to make straight for some distance because eventually it's going to end up being straight. So I'm just going to pick a random number. I like to pick instead like 69.546 like I hear. I'll say 65. And now we're going to draw a curve between this point and this point. We'll finish that. Now this one I want to be perfectly flat as it leaves here. So I'm going to grab this handle and kind of angle it down, and then I'm going to throw a horizontal vertical constraint on that handle right there. Boom. So now that's going to come out, and it's going to be straight and allow you to stick something into this path. This one I want to be tangent. So this line, I want it to be tangent to that. So there's no kinks. So I put a tangent constraint on it. And now it's just a matter of adjusting these handles so that the path doesn't go through my magnet. And it's just a little bit of a, let's see here. I think that will work, maybe a little higher. And obviously you want to make this one this transition as smooth as possible, so you're not creating a kink or a bunch up in your inside your tube, because this is basically going to constrain like a Bowden tube, your filament. All right, so I'm medium happy with that. And the next thing I'm going to do is just create a random line down here and I'm going to extend this line off the bottom of my model. And the reason I'm doing that is when I create this cut, it's going to go along this whole length. And if it ends right here, it can create funny geometry, and we don't want that. So you can see there's my line. And probably the easiest way of doing this is to create a pipe. So path is the one we just made. And the size is, I'm going to say 2 millimeters for 1.75 should give enough without too much room to make that nice slicing hole in there. So objects to cut, always look at this. Make sure it doesn't have any extra things in the way being cut. Right now it's just the lesson arm, so I'm going to hit that. And then we have, if we look at our, in fact, I could probably do this, edit sketch, and then slice sketch again. And now you can see we have a path that doesn't go through our magnet and allows that filament to push on that whatever is on the other end of this tool. Now, right here, you can see I've got this giant oversized space in my gear. I don't need it for this. So we can address that pretty easily. We said that we wanted this to be, get rid of that sketch. We wanted this. I'm going to hit the I key for inspect. And you can see this is a 3 millimeter hole. Well, we said we wanted it to be 2.2 millimeters. Although I'm not against having it a little bit bigger in the beginning to make it easier to put it in. But let's just go ahead and make it 2.2 millimeters. So I'm going to use the offset faces command. I'm going to hit Q, offset faces. And when you're doing a circular or curve thing, it's always going to be the radius. So I can type 1.1 because I can do half of 2.2 in my head, but let's just say I couldn't. 2.2 divided by 2. It does the math for me, and you can see now if I inspect this, inspect, 1.1 is the radius, 2.2 is the diameter. And we're going to apply the same treatment here, except we don't have to go through all the perturbations. We know it's 1.1, and there we go. So now we've got all this work. What is it going to look like? What tool are we going to put on it? Well, I thought it'd be cool to have a claw. And so I modeled this up a little earlier, and it's going to have some way that these all grab onto, and then my filament is going to be a plunger that captures the tines of these little things, and it'll push it up and down, open, close the claw. That's the thought. So I'll talk a little bit quickly about how I modeled this, because I know we're kind of running towards the hour mark here. And how I chose how I modeled this. So let's go back to, let's see. Here we go. So how did I choose this spot? Because half of Fusion is figure out what plane to put your sketches on. You know, that can be the hardest part. Is how do I know what shape I want, but how do I anchor to something? So for here, I'll bring Chopper's tool back up just for reference. Interface arm mirror and bread pan. So I wanted this tool to live inside a Chopper bread pan arm, which is fairly tight. So the first step was to, since it's a tri or three-piece tool, is I wanted to be the most constrained section of that tool to fit inside Chopper's arm. And I figured that would be in the back. So you saw how I used the plane at angle tool. I'm not going to necessarily do it again here, but plane at angle. And see, this time it picked the wrong angle. So let's make it 90 degrees. And that perfectly bisects that place. And that's where I began my sketch. I'm going to go back to edit sketch here. And for some reason it twists it sometime. So although I didn't use that plane, that's how I derived where this was going to be. And then I brought my bread pan in and I used the slice sketch command again. Oops, wrong sketch. Hold on. Which sketch am I actually editing? There, slice sketch, edit sketch, and slice it. There we go. So we've got this other stuff inappropriately showing up. There we go. So I just started sketching out where I wanted this, and so it would have room on this back wall. And that's how I kind of made how big it was going to be. The only interesting things here is I used the tangent command to connect two Bezier curves together and just kind of eyeballed the rest of it. And this was all based on the ice grabbing tool or ice picker upper of a tool that you can buy off of Amazon, which or you can now buy off Amazon, but was an R2D2, one of his tools. So I created that shape with the nominal spot somewhere here. And then we'll turn that pan off. Then I just extruded this. And for this, I want it to be symmetrical. And I want it to be 3 millimeters thick, because I think that's enough to hold its own, create a new body. And that's the tool. And then simply create pattern, circular pattern in the object. This can be tricky. See, if I do that, the object, quote unquote, is just that face. What I really want is the whole body. So I'm going to click on the whole body. The axis is simply going to be this tube. And 3 is the right number, but you can put any number you want in there. And there we go. Now, ultimately, and I know we're just about out of time, ultimately, I would take each one of these and make them components so I could do my animation of my stopper coming down in these joints and get the proper motion limits of how far I need to move my strand to make those things open and close. And that's pretty much what I had prepared to talk about today. Any questions? Comments?
Anyone?
Yeah, I had a quick question about the kind of a follow-up to the last question about the gear ratios. With Fusion's ability to do electronics, can you simulate or calculate the current draw based on the tooth count? Or do those two components of Fusion not work together?
They may, if you're putting in, like if you know how much that servo is working. I mean, I haven't gotten into the actual engineering side of what current that, you know, because you'd have to have physical components that you had in mind and know their properties. But I guess ultimately what you're asking is, can you determine the stress on those gears with the weight of what it's trying to do? Is that what you're really asking?
Yeah, effectively, like whatever, however the weight of the tool times the the current draw to basically to calculate how much more battery power adding this is going to require effectively?
That's kind of beyond. I mean, those things could be derived, but and there's a simulation workspace where you can do the stress and cooling. I mean, I've never messed with this, but I would submit that the amount of work it would take to do all that would be kind of lost in the fact that it's not very much. And it
Easier
depends
to
on how-
wire it up and measure than it is to simulate. Check.
Yes, at least with my limited knowledge of the electro and mechanical side of the Fusion platform. Like I said, there is a whole simulation suite that when you bring that up, you can see all of the things that it can do for its where you put in the parameters and let it create a study. But I've never delved into that. And there's also a circuit, like electronics end of it, that I've also not worked with.
No, I mean, from my perspective, I tend to just do trial and error, which is and experience. So you kind of get an understanding of what a standard servo will pull. You get an understanding of what a 25 kilo servo will pull. You tend to learn by underestimating how much power you actually need, and then having to upgrade it. Luckily, the components are so cheap that you kind of just end up having to replace and swap out. But what Tim's doing and what I'm doing is more around balancing the time that it would take to do all the mathematical equations against the time it would take to 3D print something, stick a servo on it, and then just measure the output. And to be honest, it's more measuring the output that kind of works the quickest way and the most efficient way for doing that. If we're doing it kind of on a commercial basis, then maybe all of the tools and calculations, I've not delved into those either, Tim, to be honest.
Yeah, because this is more of what I would call this is industrial design, not industrial engineering. I'm not engineering anything. I'm just designing systems that work together. They're 3D printable. Throw in some bearings and some nuts and bolts, a couple of servos, and you have a thing that that does something. And you can make this all at your house. And so that's kind of my goal, is the wide scale prototyping, if you will. Because even though I can work out all the designs and I can make my prototype work, that doesn't necessarily mean that it's a good enough design that you can just make it like a microwave, put the popcorn in for 2 minutes and pops out a tool. You're going to have to, the further my designs are refined, the easier it is to have that, print and play type of a experience. But what I found is these tools in particular, the tolerances literally go down to 0.1 millimeters. And if that 0.1 millimeters is there, it doesn't have clearance and it rubs. If I go 0.1 millimeters the wrong way, now it's too loose and it wiggles. So even though it's made of plastic, the tolerances really are quite tight, particularly when you start getting into these little bitty workspaces like choppers, like this here. As you can see, there's just not a lot of room. And when you throw that into a astromech, let me just save what I've got going here.
While you're setting up for the next section that you're going to show us, Tim, it comes to mind that the discussion where someone was asking earlier about the magnet slippage, that made perfect sense, I think. But as soon as you had that 2.2 millimeter diameter hole that was needing to be perfectly aligned between those, I would think at that point, wouldn't you want to have some kind of a locator pin or something to keep that from sliding? Otherwise, that filament becomes what's going to hold those two parts in relation to each other in the proper alignment.
Yes, this design does need a couple of splines to make sure that the magnets are going to attract themselves very reliably and comfortably, but they can also be a little bit offset. So yes, there's going to be a spline to help carry the load and align those two parts together. Absolutely. So, and this is what I mean by just you don't have any room. These droids look big on the outside, but they really are very, very size constrained in your available space. So body. I'm sorry, just catching up with myself there. So that's kind of what I'm working on right now. And as you can see, with a car dispenser and a couple of tools, and one more that needs to go in there, choppers. Interface arm is going to go in there somewhere. You can see these, you got to be kind of economic with the amount of space you are taking and try to get as much done as you can with as least impact to the local environment, if you will. Anyway, I guess that's about an hour, and I'm happy to go longer and answer questions.
Yeah, it's been great, that, Tim. Thank you. I think the other thing, just to add as well, is it just reminded me when you started to talk about using choppers arms in Duo, is the more you design stuff, the more you do servos, and I guess you do the same, Tim. I've got a workspace that's literally got all of the components I previously designed, as in all the screws and all of the servos and all the motors. So, because you do build a library, don't you, for stuff that you can actually reuse?
Yes, and one great resource for actual components is a place called GrabCAD. So they have like this motor I think I got from GrabCAD, but when I brought it in, it was the wrong size. Like, so it was a great starting point, but just because you get someone else design it doesn't mean that it's going to be accurate to reality. They may have gotten a different model, a different version, but the one I got off of GrabCAD didn't have these little wires, which are important to make sure those are oriented properly for your mounting spots. And other places, like this is a Vex wheel, they provide the step files for you, which is handy, and those should be accurate. So I'll look around and find stuff that is common parts, like for example servos, and what you can see over here in my little you can see a lot of those little pieces are living in my recents as well. Yeah. I haven't put them all in one project or one folder, which would probably be helpful.
Oh, brilliant. Cool. Any more questions? Otherwise, I'll press the stop recording and we'll wrap the session up.
All right.
No, all good.
Not a question, but just well done, Tim. That's great. Thank you.
You're welcome. It was fun to do.
Oh, very cool.
I was going to say, you and Michael obviously chuck these things out, you know, in your own time. You just like done, job done, but articulating it to a novice like me and making it sort of understandable is great. So thanks for that.
Well, I like teaching stuff. So if to that end, if this is useful, I'm happy to do more or pick other specific topics that like this one was quick and dirty on a lot of different stuff. If people need to delve into a more specific area or something, happy to do stuff like that.
I must admit, I'd like to see how you connect the claw to make it actually grip.
I'm interested in how that
in the next session.
That's a cliffhanger at the end of season 4. That you have to see that in season 5.
That'd be definitely a cliffhanger.
Brilliant. Right, I'm going to hit the stop button.